right? And any IO device looks like this. There is the same configuration which you will see in any IO device anywhere in the world. It has a set of data registers. Here I've shown it as one register. Your book also shows it as one register, but it could be a set of registers. There are a set of status registers. There are a set of control registers, right? And of course, there is the peripheral itself, and the peripheral does something useful, like keyboards take inputs from a mechanical contact closure, right? And display characters, display points, display lines between points, etc., etc. There are varying levels of intelligence to the display, but a basic display displays something you tell it to display, like a character or a point or a figure or a digit. Then we told the story about the masons, the building, and of course what was it we mentioned yesterday? Something very vital.
Gamcha.
Gamcha.
Correct.
Storage.
Gamcha. You know, this word gamcha, it may bring a smile to your face, but the way to remember something is to associate it with something unusual. So if I said status flag, it's not unusual. It's something which is very much within your professional lexicon, right? In your dictionary. So you will not remember it very well. But if I say gamcha, you will not forget it. So one of the tricks of remembering, and remembering is a tricky job, is to associate what you want to remember with something peculiar. Your brain never forgets something peculiar, right? For instance, suppose you had an uncle who ate porridge while he was upside down. You would never forget that uncle. But you have tens of uncles who eat porridge the right way up, and you'll always forget them. You'll mix up their names. So you see, the gamcha has a teaching significance far beyond its hilarious consequences or connotations. Right? So status flag is gamcha. So the mason ties a gamcha to the pole to signal to the cement mixers that I need more cement, I need more bricks. So that is what we called a status flag, and that was what we put in the status register. And we went on yesterday to the point where there was a flag like this, right? A bit in a status register, and that was the gamcha. So this is where we were. We talked about input devices, and we talked about the type of code. I think, Professor Dogra, you have to switch on the recording. Ah, yes. Okay, thank you.
Yeah, it has automatically started.
So thank you. So we also need that loop of code which you have to invoke to get this byte in and into R5. So we for the first time talked about these little pseudo code snippets. And then we went on to look at an output device and its pseudocode snippet. And we pulled it all together and we said that you keep on polling the device, and when the status gamcha becomes 1, you then either read or write to the device. And we left it at this happy note, but we also said it's not a very happy note because you don't want the processor, which is a premium thing in your computer, to wait all its life for a peripheral to become available. Because, you know, peripherals very occasionally become available, right? From a processor's point of view. So a processor could be potentially doing many useful instructions while the peripheral becomes available or has something to say. So why wait for it? So we don't like waiting. So we then took the two loops here, the read wait loop and the write wait loop, and we put it together and we said, if we highlight the troublesome part of this whole process, it's not very happy. We don't want to wait in loops, and therefore we want to do something else which cuts out the loop. And that something else happens to be interrupts. Right? So we learned just this much. IO devices look like memory devices. Right? So If you look at this, for instance, this address is a memory device. Even though it happens to be a register inside a peripheral, it looks very much like a memory location. So if you read and write to this register, your processor does not actually know that it is reading and writing to a register inside a peripheral. It can be fooled into believing that it is actually writing into a register somewhere in memory. Right? So really speaking, the display data register is very much like a memory location. Right? Of course, if you put a display data register at this location, you must not also put a memory at that location, because then you confuse the processor. When it tries to access, let's say 4010, it should uniquely see one register there. It should not see a data register of a peripheral and a memory location. So that AND part is to be taken care of by you, the designer of the computer and its organization. Right? So the uniqueness of the mapping, you take care of it. But what happens is that they do look like memory devices, so we call them memory mapped I/O devices, right? So what I'm actually saying is, okay, so that's yesterday's drawing, and I'm going to send it to Professor Dogra, so I'll keep it. What we are saying is that if you have a processor, C, and you have a set of memory locations, right? I'll just draw it like this: a set of memory locations. Forgive the indifferent lines I'm drawing, but these are a set of memory locations. And if I have 1, 2, let's say up to 128, right? I don't like to start with 0 and end with 127, because then I have to constantly subtract and say that, okay, I started with 0, so there are 128 bytes. So let's number it 1 to 128. Now, what I'm saying, therefore, is that, okay, in this so-called memory space, right? That's a nice name to give this, like a vector space. This is the memory space. So in this memory space, I could actually have memory, right? Let's say the first 32 bytes are memory, right? And then I could have 3 registers, right, which actually belong to a peripheral. So imagine these as belonging to a peripheral, right? And I am making sure that there is no memory where the peripheral is, which means that my next bit of memory actually has to start from here. And that could be, let's say, 64 bytes. So you see memory, and you see peripheral. So that's P. So since you can map memory, peripheral, memory, we call this memory mapped peripheral. So you see a peripheral sitting inside the memory space. So we call it a memory mapped I/O peripheral. Is that easy to understand?
Yes, sir.
Is that Sushant?
Yes, sir.
I think I am getting a very Sushant specific from your class. I don't think there is there anybody else in the class? Or are
Yes,
you all?
sir, it is clear.
Yes,
Yeah,
sir.
there are 63.
It
63
is
including me.
63, and I only hear one Sushant since yesterday. What happened to the other 62?
No, Satya Sangram was there yesterday discussing, and then Jagdish was also speaking yesterday. Today, actually, still they are booting up. I understand. Their system
They are booting up. You mean they are not awake?
something. I mean to say that they will ask questions. Okay.
Okay. All right. So peripherals which sit in the memory space are called memory mapped I/O devices. So that's a simple way of describing them. And but you could also do it in another way, right? For instance, you could actually say that, all right, let me have 2 spaces, right? This also goes from 1 to 128, right? But now what I will do is I promise not to put any peripherals in this space. Right? So I'll just remove these peripherals. I'll actually also remove this green thing because that happens to be a peripheral. Right? And what I'll do is I'll bring a little thingy out from here. Right? What is a thingy? A thingy is a little wire which I say is either an IO or a memory. And whenever it is, let's say, low, this wire, I select this fellow. Right? And whenever it is high, I select this fellow. Right? So depending on whether this particular wire is high or low, so let me connect this wire to both of these. So if it is low, this fellow gets selected. If it is high, this fellow gets selected. So you see, I can now put out a 1 or a 0 on this wire coming out of my CPU or processor and select two spaces. Right? One is a memory space, right? A memory space, and the other is a IO space. Okay? Now, it's sometimes processors do this, right? They actually bring out, the manufacturer gives you a wire like this, which allows you to choose whether you are actually addressing something in memory or you are addressing something in the peripheral space. So we call that an IO peripheral space, right? But then if you have the peripheral which I had put here earlier, right? This peripheral, just a second, I am still fighting with Microsoft Whiteboard. Okay, this peripheral, if this peripheral actually sits here, right, and many other peripherals like it sit here. Oh, that's nice. It's rotating. I want it to shift. Fine. So many other peripherals sit here. We make a rule that since we have a very definite IO and memory space separately denoted, peripherals, peripheral space, memories, memory space. Of course, within the memory, you can have different types of memory. So you could have SDRAM, you could have SRAM, you could have DRAM, you could have DDR-RAM, you could have VRAM, you could have RAM bus. So all sorts of memories can sit in the memory space, but memory in memory space, peripherals in peripheral space. So that's a distinction which some processors like to do. Sometimes they justify that by saying, okay, peripherals are slow, right? So when peripherals are slow, you can actually take care of the slower things in a different way, and memory is fast, so you take care of it in a different way. So sometimes what we do is we stick a memory controller here, and we stick a peripheral controller here. And I'm sure Professor Dogra remembers what is a peripheral interrupt controller. I don't. I think it is 8255. If I'm not.
Yes, 8255. Yes. I'll explain then that chip. So
good. So 8255. That's a long time back, 35 years back, right? But a very versatile chip, very useful. It's very for my children's school education for the last 35 years because I understood that chip. Right? So now, you actually put a peripheral controller and you put a memory controller, right? And you treat them differently. So that's not too difficult to understand. But very often we don't want to have these separate spaces, right? So we don't put this IO pin, fine, and we try to keep this as it is by saying, oh, it's all the same. That the address space is so big anyway that how does it matter if you dedicate these 3 little register spaces to the data, status, and control of a peripheral? It's a very small thing for a programmer or a designer. You have so many addresses available. So what we do is we map the peripheral there, and we take a little bit of care while designing so that we do not put memory also there. Fine. And that solves our problem, especially when you have itsy-bitsy processors and microcontrollers. One doesn't want to have the pain of having another wire out here called IO bar M, right? This wire, is going to stick out of the chip. The manufacturer is going to pay, let's say, 0.001 cent extra to put that wire. And when he sells a billion devices, 0.001 cent into a billion is still about $10 million, right? So why put a wire in the processor when it's not necessary? So we can actually have smaller chips if you avoid that wire, and it's good enough anyway. The little things we work with nowadays, what is fashionably called IoT, right? Which we have worked with for 30 years, incidentally, the same IoT. That fashionable little thing needs to be small, so you need to cut down on the number of wires. So we prefer memory mapped IO. While we can have IO mapped IO, so that's the second thing. IO devices could also have their separate IO address space. So you would have a physical build called IO, and if it is 1, it is somewhere in IO space. If it is 0, it's somewhere in memory space, right? So that is a fact. I think 8085 also has that, right? 8085 or its more capable cousin Z80, right? Also has that. These are all very old devices, but they are very good devices to teach a class on, because the simpler the device is, the easier it is to explain, right? This is true of many subjects. For instance, when neurobiologists look at brains, they don't look at human brains. That's very complex. They look at the brains of worms, earthworms, fruit flies, Drosophila, right? That's a simple brain. So we look at simple devices to understand things, and then we use complicated things when we need them, right? Just like earthworm's brain, human brain, we have 8080, right? And the i7, Intel i7. That's the thing which goes into your laptops, right, or your desktops nowadays. So this is where we were last time. So, just when we finished yesterday's class, Professor Dogra promised some Sushants in this class that he would show them 8279. I'm using the word Sushant as a collective noun to.
Yeah, you can use his name as a group.
So to denote all the interested students who would like to look at 8279. So all the Sushants can actually look at 8279, and 8279 has a data sheet like this.
Right.
So
I'll show them 8279, 855. Both the chips I'll show them.
Very nice. So if you really look at this, right, you will find that there is somewhere there would be a PDF, and you would be able to see this PDF like this, right? If you go down, right, it'll look like a complicated document, but then I told you yesterday that you don't have to be afraid of complicated documents. You see, this is a 16-page document which describes a chip, which is a dual inline package, 40-pin chip. But when you look at this chip, you don't say, "Oof, such a big thing! So many numbers, so much stuff in this chip," right? And this is like what I would have reacted 35 years ago when they showed me this chip. And my next question would be, is it coming in the exam or not, right? So don't ever ask those questions, because what I'm telling you is, when you look at such a chip, cut the clutter. There is a lot of clutter here. There are 40 pins and their descriptions out here, but you must learn to cut the clutter. How do you cut the clutter? Well, one good way of cutting the clutter is to look at this view of the chip, this one. Instead of this one, this is the physical view. Look at this one, right? And if you look at this with a unbiased, unjaundiced look, you will see that, oh, well, does this look like what Prof Kar has been talking in this class so far? Well, it does seem to have a data bus. That's wonderful. Does it have an address bus somewhere? Yeah, probably this is an address bus, probably, right? Does it have a thing to say it's reading and writing? Oh, well, is there a read and write somewhere out here? I don't see a read and write. Oh, yes, there is a read and a write, and they are two separate pins, right? Both are asserted as low pins. So you have to put read, right, as low in order to read, and you have to put write as low in order to write. And you have to put chip select. You have to pull it down to make this chip come active. So you have So to tell the chip, hey chip, I'm talking to your data registers, you have to pull this pin low, right? So wonderful. We have already understood 8 of these pins and 2 of these pins and 1 of these pins. And then A0. Oh, A0, it sounds like an address pin. Is it an address pin? For that, you have to go down a little bit and read this. The table which describes the 8279. For instance, the A0 is explained as pin number 21. A high on this line indicates the signal in is to be interpreted as a command or a status. So if you read this line and a low indicates that they are data. So if you read this line, you go back and you say, well, oh, well, this line then says, is it selecting a data register or a status or control register? So that's how you make your connection to the thing you are seeing. Fine. So that's the cutting the clutter part of it. Fine. Now there are going to be some pins which you can't understand, right? For instance, scan. Well, Subrat Kar never talked about scan. Throw him out of IIT Delhi. No, go and read this table. Fine. Go and read this table. There must be something more, right? Professor Dogra said, or Subrat Kar said, that all devices have some special things about them, and those special things need a little bit of stretching of the interpretation. So look at this. Look at this. It says it is a programmable keyboard oblique display interface. So this fellow, this little chip, 40-pin chip here, not only interfaces the keyboard to the processor, but it also displays a display to the processor. Oh, is it a display like my laptop screen? No, it's not that complicated. It's one of those simple displays. It's a single 16-character display. It's the type of display Professor Dogra will show you when he shows you the 8085 kit, right? So if you look at this, right, you have to then understand that, okay, part of this chip is actually for inputting. That's the input part. Part of this chip is for the outputting. So that's for the display part. Oh, so this chip is a combo chip. It's a display chip, which is output. It's a keyboard chip, which is input. That's very nice. And why did they do it like this? They did it like this because, right, when we were young, right, we tried to put as many functions into one chip. So if you bought a 60 rupee chip, right, you wanted it to do two things: get your input from a keypad and put your output to a display, right? So have some patience and go forward. Don't get afraid that there are 16 pages. Go a little down like this. All of these are important, but I'll just go down to where there is a diagram which is a little bit more explanatory. Right? The entire purpose of this showing you is, well, if you look at this, the processor is this, so that's the C I drew. This is the peripheral 8279, and this is the input. So this part, right? I am sorry I don't have a annotator which can draw this, but this part, the keyboard matrix 8279 processor, is the input part of it. The display, peripheral, and processor is the output part of it. So this 8279 is both handling this matrix, this switch matrix with 9 pins like a phone keypad, and getting that into the processor. It is also taking things from the processor and displaying it out here. So it needs both things, right? So the scan lines, now you can see what those scan lines meant. There are 4 scan lines and they go into a 3 to 8 decoder. So this is a mux which takes in 3 inputs, right, and produces 8 outputs. And the same 4 scan lines go into a 4 to 16 decoder. It takes 4 inputs and produces 16 outputs. So now you have been taught in digital electronics about N2M decoders. So now here is an example: 3 to 8 decoder and 4 to 16 decoder. Right? Merely takes these lines and produces the corresponding high output pin. Right? And then now if you come back to your first page, and be prepared to come back and forth in a data sheet, because that's how professional engineers work. Now when you come back, you can now say, okay, my cutting the clutter is a little easier. These things, the three things I see, the fat arrows at the bottom are for the display. The single fat arrow and this is for the data. Now it's not so difficult to understand that we are actually talking about a very similar device to what we were talking about here. Right? This is the same display and the same keyboard we were talking about, except that it looks a little hairy out here because it's made by Intel, and Intel has to say everything about their chip. They can't make it colorful like my PowerPoint slide, right? Whereas I can color these things, hide the details, not show you the addresses. So I can afford to make it colorful and playful, but Intel has to be professional and detailed. Now, if you have the courage, and you should have the courage, please go down and read this table one by one, right? Don't be impatient, read the table and try to say, okay, where are those data buses and where are those control buses and where are those status buses? Everything is explained here. Everything is explained here. So please do read it line by line, and you will find yourself understanding more and more from this particular chip. And every chip has a data sheet like this, right? And these are the block diagrams of what is inside that chip. And the same diagram which you saw here, right, has to be looked at in the context of this diagram. So I suggest you take a printout of this page and look at it when you are looking at the data sheet of this page. Right? See, because 35 years back we had an advantage. We used to read these things in books. When I say we, I'm referring to old hoary-headed fellows like me, Professor Rajakumar, right? We had books. We didn't have PDFs. So in PDFs, it becomes difficult to hold a page side by side or to turn quickly from here to there, right? So, but take a printout and read them side by side. Fine. I'm sure you can figure out how to read them side by side, but I will assure you within these documents, you will find your data registers, your control register, your status registers, all of those things I told you will be in this document, in this single document. And each time you see that register and you say, oh, that's a status register. Okay, it's a status register. It may have some details, but it is nonetheless a status register. You will say, though, that's a data register. It will have some differences because it's an 8279, but it's a data register. Then you say, well, it's not different from what this guy from IIT Delhi told us. It's the same. It looks different, but it's just the same. Right? So you will see things which start becoming familiar. And that mode, that is the mode when you turn into an electrical engineer. That is when you stop thinking, this is why I came and did engineering. This is why I can understand this data sheet, and somebody doing, let's say, history or geography cannot understand this data sheet. That is the turning point. That turning point is very important. You must bring this data sheet into your lives and have the patience to go through it one by one without the pain or apprehension of an exam in order to understand it, right? So please, I ask you to do this yourself, right? And not skip it because it is you are teaching, right? So let me go back to my slide and go back to this point. Any questions so far? I'm sorry, there seems to be something happening downstairs in my home. So you'll hear a regular boom boom. Think of it as background music. Any questions so far?
Clear, sir.
Yes,
So
sir,
next
clear.
interrupts. Will you all download that data sheet and read it?
No,
However,
sir.
however troublesome it sounds.
I will share with them. I have this.
No,
data.
I think I would request you not to share with them. You see, this is a good way of filtering the engineers from the non-engineers. Only those who download it and read it, only those who take the pain of downloading and the pain of reading will benefit from it.
Yes.
Once
Yes.
you share, once you make available things, once people don't have to fight for things, they do not treasure it. So I think you should download it yourself. If you do not download it and you do not understand it, you forever lose the right to say, IIT Bhubaneswar did not teach me anything, therefore I went and did my MBA. So you lose that right. Fine. Download that data sheet, understand it. If you don't understand it, ask Professor Dogra or ask me. But if you don't download it, never say, IIT Bhubaneswar taught me nothing. Fine. Now back over to interrupts. Now, what is an interrupt? We said polling is bad. We don't want an expensive processor which can actually do so many more things to keep waiting around in loops for a peripheral. And remember, there may be so many peripherals in a processor's domain, maybe 5, maybe 2, maybe 10, maybe 30, maybe thousands, right? 1024 peripherals, right? So a processor should not be made to wait. The processor is the king of the motherboard. Right? So let's see how a peripheral, when it is ready, tells the processor, hey processor, I'm ready. It's hey processor like in English. It's not like in Sanskrit. Hey Bhagwan, not like that, but hey means hey processor, I'm ready, that way. So how does a peripheral say that to a processor? So what are interrupts? We know waiting is not a good thing. All these statements are from Karl Hamischer. So waiting wastes a CPU's useful time. I added that word useful. So it is better to let an IO device interrupt a CPU. Yesterday I used the phrase, pat the CPU on the shoulder and say, CPU, I need service. That's what we want to say. Ask for a service, right? And depending on which peripheral, for instance, suppose you have somebody who makes chapati for you in the kitchen, right? And that person will ask you okay, sir, where is the atta? Where is the wheat? Because I need that wheat to produce my chapati. So you'll go get the wheat out of the storeroom and give it to him or her and come back. Then he says, where is the water? So you see, the wheat, the water, the salt are all associated with the making of the atta for preparing the roti. So really speaking, the service which you give to the fellow who makes rotis for you is different from the service you will give to your gardener. If your gardener comes and says, sir, where is the hose pipe? Where are those tomato plants you wanted to plant? So the service which the gardener wants from you is essentially different from the roti service. So every peripheral has a service it needs from the CPU, which is different. So when it asks for service, it is actually asking the CPU to execute a snippet of code, which does that service for it. And this snippet of code is called a interrupt service routine, or ISR. ISR, interrupt service routine. So you'll have a interrupt service routine for peripheral 1, a different interrupt service routine for peripheral 2. If peripheral 3 happens to be similar to peripheral 1, you will execute the same ISR as peripheral 1, but in a different context. For instance, suppose you have 2 people who make rotis. Then you will essentially give both of them 2 bottles of atta, but you must track which bottle of atta you gave to which roti maker. Right? So the action is the same, but the context is different. So this is what you must remember in the ISR thing. Now, before executing this service routine, a CPU must save what it is doing, the context. What were you doing when you went to do that service routine? For instance, suppose you were singing a song when somebody asked you, where is that bottle of atta? Now, so you stop in the middle of the alap and you go and give him the atta, and you come back and you pick up the song where you stopped. So that is the context. You don't resume your rag from where you stopped singing it. So the CPU resumes its rag from where it stopped singing it. Now, when the ISR gets completed, that resumption, and this is a sequence of steps. It's not just a quick word called resumption, right? And it resumes what it was doing, and this means that it doesn't have to wait ever. Okay, there's an aeroplane going up overhead, and I'll just wait for a little while it goes. And this method of servicing a peripheral when it needs that service eliminates waits completely. Fine. So let us look at how interrupts work. Now I will put it in slide mode because it's so small that without a spectacle I also can't read it. Okay, so consider the same two tasks, compute and display. Right? The processor is executing a routine called compute. This is the blue box here. There are these lines of code here. I hope you are able to see this. Line 1, instruction 1, instruction 2, instruction 3, till it comes to an instruction where the display peripheral pats the CPU and says, CPU, I need some work from you, some service from you. So when it was executing this line of code or this instruction, the peripheral interrupts the CPU. So the CPU is at this orange bordered instruction. So at this point, the CPU stops what it is doing, saves the context, and goes and does means executes the snippet of code which is supposed to do something for the display, maybe send a character to the display. So all these codes in this green box are things which are lines of or instructions to do with displaying a character on the display. When it is finished, it is at this point, it comes back and resumes at the next instruction which it was supposed to execute. So between two instructions, it goes out, does something, comes back and resumes. So the interrupt is occurring here at the ith instruction, right? So this in your textbook, it says that, well, it's not as if the display peripheral will tell the CPU that do you have something to display, because display devices don't really interrupt anybody. They are waiting for things to come to them so that they display it. So it seems counterintuitive for a display peripheral to tap the CPU and say, hey, give me something to display. If the CPU has nothing to display, then it will not display anything. So which is why your textbook says that, okay, let's not have the display peripheral interrupt the CPU. Let's have another peripheral called timer interrupt the CPU every 10 seconds. So every 10 seconds, the timer just pings the CPU and says, hey, CPU, do you have something to display? So the CPU then goes, executes the service routine and says, oh, well, I don't think I have anything to display, and comes back immediately. But if it does have something to display, the CPU is going to say, ah, yes, well, thank you for reminding me. I have something to display. And then when it goes and displays it, it comes back with the character now getting displayed on the display and resumes where it started. So this is what your textbook is describing in your example. So the processor executes the compute routine when it receives an interrupt request from the timer, not from the display. It suspends the execution, executes the display routine, and then resumes. There is a lot of blah blah in this. That's because the text is all from your book. But the sense and the principle of it is that 10 seconds, every 10 seconds, a timer tells the CPU, go display something. If it doesn't have anything to display, it immediately comes back and says, I have nothing to display. If it has something to display, it executes the display code. Right? That's not very difficult to understand, I hope.
Yes, that's clear.
That's clear. So now I have duplicated that same diagram out here. So that's the diagram out here. So there are two things. One is servicing. The routine which you execute in response to a ISR pat on your shoulder, right, is called a service routine or interrupt service routine. Very much like any other service subroutine, or any other subroutine, right? So suppose the interrupt comes here, right? It will first finish executing this instruction, right? Go and execute this and come back here. Your textbook actually just says this much, and that's actually very correct. But you know, this sentence, the processor first completes execution of instruction I, is, at least to some Sushants out there, it's going to be a little troublesome, because what does it mean, right? Can an instruction be cut in the middle? For instance, suppose in a move move immediately A, comma, something. Suppose I am in the middle of the instruction and interrupt comes, do I move or not move whatever I was supposed to move to A? I know there will be some Sushants who will have that question, and I hope there are many Sushants in your 63 member class who have that question, because that question is not a simple question and it's a very elegant question. So I think to answer that question, I digress for 2 slides. If you just go to the processor architecture of one of our contemporary processors, that's the i7, and this is something I'm taking from Intel, the makers of the i7 chip, and you go to section 6.6, right? That's in manual number 3 out of 6 manuals, and manual 3 has 2,000 pages. So I think I will have to go to the right point and show you. Either I open that PDF again or I show you the right. Okay, I think I have forgotten where that PDF is. So let me just click on this, and if you look at this, for instance, okay, let me get out of here, escape, and go to my browser. That's the 8279, and I should be able to open. I'm sorry, it's a 2,000 page document, so it takes a little time. I thought I had it on my screen. Oh yes, I do have it on the screen. That's the one. Fine. That's because yesterday night I was reading this. So if you look at this section 6.6, you do find that to allow the restarting of a program following the handling of an exception or an interrupt. An exception is a type of interrupt. All exceptions are guaranteed to report exceptions on an instruction boundary. All interrupts are guaranteed to be taken on an instruction boundary. So this is the sentence which you, in a 2,000 page document, to qualify this line. Which line? This line. This line. That all instructions happen on the execution of an instruction I. What I did was that 2,000 document is a little too fat for all of you to read. So I just took out this part, and the next slide shows you what you have been taught, that in an instruction, right, which has a fetch, decode, execute machine cycle, you can subdivide that instruction cycle into what are called T states. You may or may not have been taught, because in contemporary UG curricula, this is considered detail, right? We don't actually spell it out, but every instruction cycle has these T states. The T state is the lowest.
I have introduced this basic concept.
Okay, if you have, then this is the clock cycle of the microprocessor, right? T1, T2, T3, T4, and if an instruction, for instance, comes at T2, what that line says is it will start getting service from this point. This instruction will complete. This is the instruction boundary. So that's where an instruction starts. So if that question hit your mind, then what happens if it comes here? Will I stop here in the middle of a fetch and do the interrupt service routine? No, I won't. I'll proceed till an instruction boundary and then do the service routine. So that's the answer to that question. So now back to where I was. Okay, where was I? Okay, fine. Back to this slide. I'm almost at the end of today's class. So what I'll do is I'll just read these 2 lines and stop. It completes execution of the instruction I at the instruction boundary. It loads the program counter with the address of the first instruction of the service routine. Let's assume it knows where that service routine starts. Where is this instruction? Okay. And then after executing the ISR, it returns to instruction I+1. So there's a hint here that if you have a program counter or a program status, the program counter is somewhere getting stored, right? And it's being stored or kept on a shelf while you go and execute the ISR. And then when you come back from the ISR, you take it off the shelf and you say, oh, where was I? I was at this program counter, and now I must go to program counter +1, the I plus 1th instruction. So it's as if you are storing that program counter in a biscuit tin, and then when you come back from the ISR, you are pulling it out of the biscuit tin. And what do we call this operation where you push something into a tin and pull it out? Have you ever pushed a biscuit or a set of biscuits into a narrow tin? Like, do you eat Pringles chips? Have any of you eaten Pringles chips, or are you one of those saints who don't eat Pringle chips? Have you eaten Pringles?
I have eaten.
You have eaten, right? Oh, who's I? Is it Professor Dogra?
Yes, yes.
Oh, no. You are far too old to be the example in this example. These 17-year-old students have not eaten Pringles chips.
I have eaten because my daughter eats that. That is the reason.
You mustn't do that. Okay, a Pringles chip has a stack of potato chips in it, right? So when you put back a Pringle chip into that tin, right, you can only pull the topmost chip out. Right? So a Pringle chip tin is a good example of a stack. You push chips into it, and when you pop chips out, you get the topmost chip. You cannot reach under a chip and pull out something which is below the topmost chip. That's not possible. So this particular thing which is happening here, a program counter being pushed and popped, is a good place to use a stack. And you know that processors have stacks. They have stacks for precisely these reasons. You can have a hardware stack with a stack pointer. You can also maintain software stacks with soft stack pointers. But push and pop is a very common thing to do. And as a matter of fact, many things have to be pushed, many things have to be popped. So the sequence in which they are pushed, the sequence in which they are popped is also part of saving this context. So when an interrupt occurs, the current contents of the program counter must be put in a temporary storage. That's a push operation in a known location, a stack, which you know where it exists. And when you return from an interrupt instructions at the end of the service routine, you will resume at the I plus 1th instruction. So the return address must also be saved in that stack, processor stack. Now you may know that processors have a stack, but some processors have more than one stack because they do so many things that it's useful to have more than one stack. So we will stop here and I will take questions, right? But is it clear so far?
Clear, sir. I have a question.
Yeah.
So,
Are you Sushant?
No, sir.
What are you? Who are you?
Jagdish.
Jagdish. Oh, what a relief. Jagdish Deshmukh.
Yes, sir.
Please tell me, Jagdish.
Yeah. So if like assuming like an interrupt service routine might take at least 2-3 instructions. Let's say I'm in keyboard ISR second instruction and then I get another ISR. Do I again switch from the first ISR to second ISR, wait for completing, then take the other ISR, or
Will you have the patience to wait till Wednesday? Because I'm going to take this up on Wednesday.
Okay, sir. That we can wait if it's a topic.
Yeah, it is a topic. As a matter of fact, I can whet your appetite a little bit by saying that, okay, this is what you're talking about, right?
Yeah, interrupt between interrupt, yeah.
Right? When interrupts interrupt the interrupt handler. Right? So I put a smiley here because I couldn't pronounce it after I wrote it. When interrupts interrupt the interrupt handler. Right? So, but this is what you're talking about. An interrupt routine where an interrupt happens, inside which an interrupt happens. Right?
Or maybe another device also.
Anything.
If not,
I see. I've colored them differently: green interrupt, orange interrupt, gray interrupt. So they are from different devices, right? Okay. You see, it's the problem is not as simple. The answer is not as simple as it appears in this diagram, because here this interrupt has something to do with peripheral 1. And how does peripheral 1 know how to service peripheral 2? Do you understand that? So it's not absolutely simple if you look at it, right? But if you wish, you can just write down this link, right, and read the story there. So where is my glass of water, Narad? So that's the link. I don't know how I can set it. I'll make it easy for you. I'll post it in the chat window so that I don't have a chat window. Oh, no, that's the reaction. So where is my chat window? Oh, I'm sorry, I don't have a chat window. Somehow.
I think you are externally connected.
Correct. So I don't have a chat. But anyway, this link, read the link. This is from the Bhagavad Katha. Not that I'm an atheist, but it's a nice example of this particular problem. So we'll take it up next class. Okay.
Okay, sir.
Thank you.
Okay. Thank you.
Thank you, sir.
Thank you.
Bye.
Thank you, sir.
Bye. Thank you. We'll see you next Wednesday.